Hi. Are you guys all right?
No, we're not.
Yeah. Okay. Okay. Our project is using Jacobian sparse autoencoders, applying them to the attention layer of transformers.
I'm Julian Yard.
I'm Alina Iyer.
And I'm Wilbur, and our mentor was Brian Matt. So, for a quick run through of what we're going to go through today, I'm first going to give you guys an introduction to mechanistic interpretability, transformers, large language models, stuff like that. Then we're going to talk about Jacobian sparse autoencoders and sparse autoencoders in general before we dive into our project, and then we will open the floor to questions.
All right, so we're going to start off with a quick introduction. Large language models are massive machine learning models that specialize in language processing, and most LLMs use something called a transformer architecture. We know these LLMs as generative pre-trained transformers, or GPTs, like ChatGPT. Transformer architecture is actually used for a pretty large range of machine learning tasks, which rely on the tokenization of different elements of the input. Tokens are essentially pieces of words or characters, and the model learns relationships between them based on context.
Okay, so an overview of mechanistic interpretability. Mechanistic interpretability is a field of artificial intelligence research that's concerned with looking into the black boxes that are our day-to-day AI models. Because AIs are mostly created with self-supervised training, which means we don't really manually input the neurons in there, we don't have very much way to control the output other than just changing the algorithm. And we don't really know what's happening. So mech-interp researchers work to understand the inner workings of AI to improve their safety, debuggability, and transparency.
So transformer models are mainly composed of repeating sequences between two different types of layers, the attention and the multi-layer perceptron layers. The figure on the left displays an architecture of a basic transformer model. And there's a lot going on here, but there's only two really important things that you need to know, which are the attention layers and the MLP layers.
And for our project, we wanted to focus on the attention layer. So the attention layer is responsible for adding contextual information for a sentence. What that means is, in the sentence, the quick brown fox jumps over the lazy dog, attention might apply quick and brown to fox so that the AI kind of knows that the fox is quick and brown. And then how it does this is using three main values, the key, query, and Z values. The key and query value basically tells you how much one word applies to another. So Fox might be looking for color information. That would be a query value. It's asking, hey, is there anything about color? And then brown would be referring to brown. So the key value says, hey, I have color information, tells the query, and then that contributes to the Z value, which is the final output, and that's added to a residual stream. And so the amount of information passed over actually depends on how closely the query and key value aligns. And then analyzing these values and how they relate is what gives us valuable insight as to how attention works. And that's why we chose to focus on them in this project. There's other values out there too, but we thought these were the most important.
Okay, yeah. So our next section is going to be about sparse autoencoders and the focus of our research, which is Jacobian sparse autoencoders. So to kind of talk about sparse autoencoders, I want to really ask the question like, oh, what exactly is a feature? So a feature is essentially a representation, a vector representation of the transformer, which is a human interpretable concept. So here's an example of a feature that was extracted in Anthropic's paper on sparse dictionary learning, which they took from their Claude 3 Sonnet model, I believe. So this is the feature that they extracted for Golden Gate Bridge. Anthropic's mech-interp team noticed this feature occurring within the model on tokens relating to the Golden Gate Bridge. So you can see the tokens here that are highlighted are tokens that we're recognizing as being correlated with the feature of the Golden Gate Bridge. And this also occurs on other languages. So the question is like, okay, how did they actually manage to extract this feature?
And to go into the answer to that question, we'll have to talk about superposition and semantic features. So the process of extracting semantic features like the Golden Gate Bridge is actually a major focus of mechanistic interpretability research. And mech-interp researchers quickly noticed that it's really hard to isolate features by themselves. This is because representations in the transformers are entangled, which means that individual neurons actually correspond to multiple different semantic features in a process called superposition. And this is when the model learns more features than it has neurons, and thus each individual neuron corresponds to multiple features. So if we look in this graph, you can imagine each axis corresponds to a feature. These first two pictures represent a neat world where every dimension maps to a feature cleanly with no interference. In a two-dimensional plane with two distinct features, this works well. Unfortunately, it would be completely inefficient for AI models to only have as many dimensions as it has features. So, because they end up only having thousands of dimensions and there are maybe millions of features, no longer can we cleanly map one feature to one dimension. So what we see here is some interference going on where there's more features than dimensions, and that results in some interference over here. This poses the question, oh, sorry. One example of how this might work in real life is that one neuron that activates strongly in response to basketball players might also react strongly to North Korean dictatorship because they're very distinct subjects. We'll see that it only has to respond in one context, so that's what happens. And this poses the question, how can we access that higher dimensional feature space from our neuron activations?
And this is actually done with something called a sparse autoencoder. So essentially, a sparse autoencoder is a neural network that is trained to create a sparse high-dimensional representation of the model's neuron activations, which is like a sort of feature space. And it is also supposed to be able to be decoded back into that dense, low-dimensional transformer vector space. So the sparse vector representation is sparse in that most of its values are 0. And given that what we understand about normal transformer space being insufficient in dimensions to represent semantic features discretely, this sparse feature space is a really good way to extract and interpret semantic features. It's also possible to take a singular feature from that hidden layer of like a very high dimensional sparse hidden layer from the sparse autoencoder and put it into the decoder element of the sparse autoencoder by itself to get a dense low dimensional representation of that feature, which you can use to tweak certain features in the model and clamp them to higher or lower values, which is really helpful in safety and debugging features. Sparse autoencoders are very, very helpful in identifying the existences of certain features at certain points in the model. But it would also be really helpful theoretically to be able to take the features before some part of the model and then take the features after some part of the model and then compare the interactions between them, because then you'd be able to see essentially how that part of the model works to compute the set of features B from the set of features A. And this is what Farnick et al. 2025 did in their paper about Jacobian sparse autoencoders. Essentially, Farnick et al. Developed a method for creating a sparse computation graph between interpretable features. And their method was called creating a Jacobian sparse autoencoder or a pair of Jacobian sparse autoencoders. So by doing this, they're able to show for a certain part of the transformer which input features are used to compute which output features. And in order to do this, they trained two sparse autoencoders, one immediately before the multi-layer perceptron layer of a transformer and one immediately after, and then calculated the Jacobian, which is essentially, if you're not familiar with what a Jacobian is, it is the derivative of a vector function. So they're able to see how each element I in the first set of features influences the computation of each element J in the second set of features. And part of their training of Jacobian sparse autoencoders, they included the sparsity of the computation graph in the loss term, which means that they were able to create these really easy to compute and easy to interpret computation graphs between the feature set A and the feature set B. I guess they use X and Y here, but you get what I mean. So this first thing you see on the left here is a computation graph that you might take between two normal sparse autoencoders. It's very complicated. It's very hard to compute because you're going to have a lot of features. But for Jacobian sparse autoencoders, it is a very easy computation to do. And you're also able to see, oh, how is this feature for the first sparse autoencoder able to influence the computation of the feature for the second sparse autoencoder. And so here's how this might actually look in practice. So actually, this is how it does look in practice, because this is from Farnick et al.'s paper. But you can see that these three green bits here on the right are actually features taken from the first sparse autoencoder before the multi-layer perceptron layer. And then this pink feature right here is one feature taken after the multi-layer perceptron layer. So essentially, you have the first one, which is a feature that activates on instances of the city of Berlin. The second green feature, which activates really strongly on any mention of German. And the third feature, which activates really strongly on the part of German surnames, which is von. And so both of those, or all three of those, had a very high relation in the Jacobian to this next feature, which activates really strongly on German tokens. So essentially what the model is doing here is learning that these three things are essentially mean that German text is likely to follow. Yeah.
Okay, so now we're gonna go into our project and what we've done throughout this program. All right, so our main motivation was to better understand the internal circuits of transformer models. We wanted to build on recent progress on SAEs and Jacobian SAEs, which were actually introduced during our program around a month ago. And we thought it would be really exciting to incorporate such fresh research into our work. The recent JSAE paper only explored understanding the MLP computation, and we wanted to focus on understanding the attention computation. And our main project goal was to train SAEs and JSAEs on the inputs and outputs of the attention to disentangle both its features and computation to make it interpretable.
So to explore more about how the attention activations affect the output for SAEs and Jacobian sparse autoencoders, we trained two sparse autoencoders on the different internal activations of the attention model. One model was trained on the query values and another was trained on the Z values. And then we compared these two to an SAE trained on the MLP output. Then we worked to train Jacobian SAEs on the query and Z values to understand how query features are used to compute Z features. After weeks of running out of compute in Google Colab, this probably happened 6 or 7 times, here we are. So this is the SAE trained on Q values, and this is the SAE trained on Z values. You can see that they're very similar. And then this is the one trained on the MLP output. And what we notice here are two observations mainly. So while all of the SAEs generally follow the same training pattern in terms of loss, where we see that like the loss goes down after a initial spike, there's a noisier L1 loss curve when comparing the Z and Q values to the MLP one, which means that the sparse autoencoder isn't as capable of consistently seeing the most important feature. This is likely because of attention being generally more fuzzy than MLP. And there's also higher reconstruction loss, which means it's harder to compress and reconstruct the data. And this instability may stem from just the more dynamic and context-sensitive nature of attention, once again.
All right, so this is a feature-centric visualization of what we explored, and this image is specifically for feature 0 of batch 0, one of the many learned features in our SAE. Each highlighted token in the sentence shows where the feature was strongly activated during inference. Brighter highlights mean stronger activation, so we can interpret what kinds of patterns or context this feature is detecting. Visualizations like this help us better understand which neurons in the original model are being captured by the SAE and how these neurons respond to different features and tokens. All right. We also began training a new type of Jacobian sparse autoencoder, which calculated the inference of features trained on query values of the attention head and on features trained on the output values of that head. Essentially, this allows us to see what each token looks for and how it computes the features of the vector it produces for any particular head of attention, an incredibly valuable tool for understanding the function of the head. Training a Jacobian sparse autoencoder is an incredibly difficult because of the need to calculate the large computation graph, which is the Jacobian, in high volumes throughout the training. In order to get around this, Farnick et al. Developed an analytical formula for the computational graph, which you can see on the slide, and implemented it using the INOPS Python library.
So we actually had to change this around because we are using the attention head computation instead of the multi-layer perceptron computation. So if you kind of want to see the differences between our function and what they did is they had the encoding weights for their sparse autoencoder. I believe it was, let me look back for a second, or for their second sparse autoencoder, the output weights of their multi-layer perceptron, the Jacobian of the nonlinearity function for their multi-layer perceptron, the input weights for their multi-layer perceptron, the decoding weights for their input sparse autoencoder as their terms, and we had to replace it with terms that were relevant to the attention computation, which was the input. Of course, we kept the weights for the sparse autoencoder, but we had to replace the weights for the multi-layer perceptron and the nonlinearity with our key values, which were trained off, or not trained, sorry, which were computed off of the WK matrix, which is learned by the model, and the derivative of the softmax of the attention pattern, and then V transpose, and then the rest of the terms are the same. But yeah, it took us a while. It was like a really big part of our project to implement this using the INOS Python library.
Alright, so we haven't yet managed to extract and compare the interpretable features from attention heads, but you can see here that we did manage to begin the training and start to get results for decreasing the overall JSE loss. And yeah, we'll now open up the floor to questions.
So like the thing, prime that is very, very helpful.
Answered a lot of questions.